Find the minimum cost for 1 cubic yard of fertilizer. In this problem, a 1 cubic yard mixture of fertilizer is to be created which has at least 10% nitrogen, at least 6% phosphorus, and at least 10% potash. There are a total of 13 raw ingredients of which the fertilizer mix can be composed. Each ingredient has a known percentage of nitrogen, phosphorus, and potash, and an associated cost per cubic yard. The first ingredient is fish scrap. The variable x1 represents the volume of fish scrap in the fertilizer mix, in cubic yards. Fish scrap contains 8% nitrogen, 2.9% phosphorus, and 0.9% potash. The cost for 1 cubic yard of fish scrap is $3. The second ingredient is cottonseed meal. X2 is the volume of cottonseed meal in the mix, and the percentages and cost are shown as well. The third ingredient is nitrate of soda, and the fourth ingredient is sulfate of soda. Ingredients 5 through 7 are urea, bone meal, and phosphate. The remaining 6 ingredients are saltpeter, muriate of potash, sulfate of potash, ammonium nitrate, potash salts, and filler material. Decision variables x1 through x13 must be non-negative, and the sum of all decision variables must equal 1 to make 1 cubic yard. In this problem, our constraints include the 3 minimum mix requirements for nitrogen, phosphorus, and potash, the volume constraint to make 1 cubic yard of fertilizer, and the non-negativity constraints. Writing out the minimum mix requirement constraints in terms of decision variables x1 through x13, where N, pH, and P refer to the percentages of nitrogen, phosphorus, and potash in each of the 13 ingredients. These percentages were shown in the table and can be substituted into the 3 constraints. To convert these constraints into standard form, surplus variables S1, S2, and S3 are subtracted from the left-hand side, and the inequality constraints become equality constraints. However, since an initial feasible solution is not trivial, we'll add artificial variables V1 through V3 to these 3 constraints. And we'll begin the algorithm by setting all 13 decision variables to 0, the 3 surplus variables to 0, and the 3 artificial variables to the right-hand side for each constraint. The volume constraint requires the total volume of the fertilizer mix to equal 1 cubic yard. Writing this constraint out, we notice our initial x vector, the 0 vector, does not satisfy the constraint. So we'll have to add a 4th artificial variable, v4, to the constraint, and set its initial value to 1. In addition to our decision variables, we also have cost variables C1 through C13, corresponding to the cost per cubic yard of each ingredient. Our objective function, z, is to minimize the cost of the fertilizer mix, C transpose x, while satisfying all constraints. Setting up our network tableau, we begin with the 4 artificial variables in the basis. To put the tableau into canonical form, we'll pivot about the 4 artificial variables by subtracting rows v1, v2, V3, and V4 from row Z1, and the values that changed are shown in red. We begin solving phase 1 of the algorithm by pricing out. We notice variable x9, which represents muriate of potash, currently has the lowest reduced cost coefficient for phase 1, and will replace artificial variable V3, since 10 divided by 57 is less than 1 divided by 1 from the ratio test. Pivoting about variable x9 involves dividing row x9 by 57, then adding 58 times row x9 to row Z1, subtracting 12 times row x9 from row Z2, and subtracting 1 times row x9 from row V4. Now the tableau is in canonical form, since column x9 is now part of the identity matrix. Now we can begin a second iteration of the simplex algorithm. At this point, variable x5, which represents urea, has the most negative reduced cost coefficient and will take the place of artificial variable v1 in the basis, since 10 divided by 46 is a smaller positive quotient than 0.825 divided by 1. For this iteration, pivoting about variable x5 involves dividing row x5 by 46, adding 47 times row x5 to row z1, subtracting 14 times row x5 from row z2, and subtracting 1 times row x5 from row v4. So far, artificial variables v2 and v4 are still in the basis. On the third iteration, we determine variable x7, which represents phosphate, will enter the basis since negative 36 is the most negative phase 1 reduced cost coefficient. Decision variable x7 becomes basic, and artificial variable v2 becomes non-basic, and row x7 is divided by 35. Next, 36 times row x7 is added to row z1, 27 times row x7 is subtracted from row z2, and 1 times row x7 is subtracted from row v4. Next, variable x1, which represents fish scrap, is chosen to enter the basis in place of artificial variable v4. After the pivot operation is complete, we have found a feasible solution of 4 ingredients for our fertilizer mix. The initial mix is composed of ingredients x5, x7, x9, and x1, which is 0.113 cubic yards of urea, 0.122 cubic yards of phosphate, 0.166 cubic yards of muriate of potash, and 0.599 cubic yards of fish scrap. The sum of these volumes equals 1 cubic yard, which satisfies the volume constraint. If we add in a column for the unit cost of each ingredient, we can calculate the cost for each ingredient in the mix and add those costs together. Our initial mixture costs $8.66 per cubic yard. This is a feasible solution, but it is not optimal. Returning to our tableau, we can remove row Z1 and columns V1 through V4 since phase 1 is complete. From pricing out, variable x6, which represents bone meal, is next to enter the basis in place of variable x7, phosphate. Pivoting about x6 involves dividing row x6 by 0.75, then adding 5.97 times row x6 to row z2, and subtracting 0.254 times row x6 from row x1. After substituting in x6 into the mixture for x7, the cost per cubic yard of fertilizer mix dropped from $8.66 to $7.70. Next, variable x11, which represents ammonium nitrate, will enter the fertilizer mix in place of variable x5, which represents urea. After pivoting about variable x11, the tableau is updated and our mixture cost reduced from $7.70 per cubic yard to $7.49 per cubic yard. Next, variable x10, which represents sulfate of potash, will enter the basis for variable x9, which represents muriate of potash. After pivoting about x10, the tableau is again in canonical form. At this point, there are no more negative reduced cost coefficients. Therefore, the current solution is optimal. The quantities of each of the 4 ingredients are shown, where nearly half of the fertilizer mixture by volume is fish scrap. As before, the sum of the individual volumes equals 1 cubic yard. Calculating the cost of each ingredient and then summing the ingredients, the minimum fertilizer cost per cubic yard is $7.42. When reviewing the possible solutions, the answer is C.